Lesson 2, displaying data and describing trends. The two main goals. The first is for you, by the end of this lesson, you'll be able to create and interpret scatterplots that result in a linear pattern, and to use appropriate scales when constructing a scatterplot. Just a brief intro here. Sometimes data that is, something you get a whole set of data, for example, a weight of a set of people versus their height, or you're looking at right now, if you're looking at a pandemic, you're looking at day and the number of infections. So that's, and you can plot those relationships. There's a relationship between 2 points. Generally speaking, these patterns describe in different ways. And in this unit, we'll be focusing on linear pattern, linear. When we see the word linear, it means a line. Okay, so when we refer to linear, it's referring to as a line. So be cognizant of that. Linear means line. The next unit, we'll be looking at different kinds of pattern called quadratics, but that's, right now we're looking at linear. But let's look at what a scatter plot. Basically, scatter plots, and this is from the website Math is Fun, and they put a link on the for this, so you can check that page out. So in a scatter plot, it has points that show the relationship between two sets of data. So here you have weight and height. So it's one person's weight versus their height. So if you look at different of a person over time, you'd find that as normally the weight increases in this case, the height also increases. So this is what you call a scatter plot, where you are showing the relationship between two sets of data. And it's a really good way of representing reality. But another thing it does, scatter plot, apart from displaying the data, it gives you a graphic representation, it can be used to make predictions. So that's the power of scatter plots. If there's a trend, and we'll look at that. Generally, you're given a set of data, and here we have examples from here. We have ice cream sales versus temperature. And we plot these on a graph. Now, the previous lesson we learned about the Cartesian plane. So we'll plot this on a Cartesian plane. And if you were to plot this set of data, temperature, ice cream sale temperature versus ice cream sales. In this case, we'll put this on the x-axis here, temperature, and on the y-axis, ice cream sales. So here we have temperature, degrees Celsius, and we have ice cream sales, number of ice cream sales, or in dollars. Sales. If you were to plot this on a Cartesian plane, this is what it will look like. We have on the x-axis, or the horizontal line, we have temperature in degrees Celsius, this label. And in this case, it started from $10. Normally, we try to begin from zero, right? So this scale started from 10, but generally starting from zero. And this is your number of dollars sales. I'll show you another example. Here I have an example of a scatter plot of, this was a person named Justin, and he earned, this is his weekly earnings from his father's store. In this case, this is our x-axis, and I'll just weeks. And it shows the weeks and the earnings. So this is another display of a data. Now, once we have this set of data, we refer to the x-axis point as the independent variable, so that we call this independent. And the x-axis referred to as the dependent. So the paycheck, the amount of money you make, is dependent on the number of weeks worked. So this is dependent. One way of remembering which is dependent, just imagine writing a big D here. That's your dependent variable. And the other one will be the independent. So the independent variable, this is the variable here, x-axis, that isn't influenced by anything. This is what you're going to say. Look, I'm going to look at how much money this person earns, Justin earned, over 20 weeks. So the amount of money he would have earned is dependent on the number of weeks he had worked. The dependent variable is affected by this. So how much money you make, you can see here, is dependent on the weeks worked. Now, what we can do now, because we call it a line of best fit. So now we have the set of data here. Go back to this graph here. We have a dependent, independent. Now, a line of best fit it's this where we have the power of this scatter plot. Okay, let me check out this right here. Yeah. A line of best fit is basically a line that we draw through the points in the graph. So you want to go through as many points as possible, and the number of points above the line and below it should be approximately the same. It doesn't always work out perfectly, so it's an approximation. So we call line of best fit. Now you can go into statistics and get a better line of best fit, but with a fair amount of calculations here. But in this case, all what you'll do, you take a ruler and you draw a line that will pass through as many points as possible. And that is referred to the line of best fit. So as long as the line fits with most of the data, so now if there's a point that's much higher or lower, right, it shouldn't be on the line. In this case, this one's really high. And this is what we call an outlier. We generally wouldn't consider that because that's an outlier. It's probably caused by maybe his father decided to give him some extra money. Maybe. Father may have given him more hours per week or more responsibility, so he paid him off, give him some extra money. So we don't know. But this would be his regular trend. So we can make prediction from this. Right. So when you see a line, when there is an increasing in this form, an increase, this is what they call an increasing correlation, and we'll talk about that in a minute. As the value in the x-axis here, the weeks increase, the value in the y-axis increases. And so this is what we call a positive correlation. So correlation, right, talks about how much these two variables are related to each other. So correlation, if I would write it down here, so correlation, we'll go over these in more detail. This is an overview. So correlation now, how much the two sets of data relate to each other. So in this case, the number of weeks related to his earnings. So once we constructed the line of best fit, we can make certain prediction. Now, in this case here, we make a prediction for week 20. Now, he hasn't worked yet, so we can say what will happen, how much money will he make, the total amount, what will his paycheck be after week 20? And using the line of best fit, we can make a prediction. So we can say here, after in this case here, adjusted earning 20th week, he will make 157. We go across here, 20th week, it's $157. So he'll earn in his 20th week $157. So that's where line of best fit or correlation, our line of best fit can be used to make prediction. Now there's correlation, as I mentioned before, positive correlation, negative correlation, and no correlation. So let's see what that looks like in your booklet. Let's jump back to your booklet now. This is a Cartesian plane, and here we have a set of data that plotted on this graph. So these are the points, right? So now, when we see an upward trend, if you would line of best fit through here, we say that's a positive correlation. Positive correlation between the x and the y variable. And because as x increases, the y increases. So if you go along here, as increases x, what happened? The y value increases. That's why we say it's a positive correlation. The opposite would be true if there's a decrease. Now we have a negative correlation. So here we see the number of absences. As the number of absences increases, the scores decreases. Right? As the number of absences increases, the score decreases. So we say this is a negative correlation. Positive correlation. Here we have our negative correlation. Now, what happens if there's no increase as the x value increases? So if we go from left to right, the y value remains the same. So we call it a constant relation. So this is a constant relation. So constant means doesn't change, the y value doesn't change. As compared to our positive correlation where the y value increases, negative correlation, the y value decreases. So it's going down a negative scale. And the last type of correlation is no correlation, because if you look at this scatter plot here, they show a random pattern. There's no pattern. There's nothing here that you can construct a line of best fit. So if it's a random pattern, there's no correlation. So no correlation because of a random pattern. Because we have a random pattern. So remember these 4 types of correlations. And correlation, remember, is how the variables are related to each other. How the number of absences in this example refer to the scores. That's what we call a correlation. Looking at relationships between 2 sets of variables. So if I say, what's the correlation between height and age? We're looking at how, as 1 increases, for example, as age increases, what happened to your height? And that's what they call a correlation. Now let's look at how we can apply correlations and linear function here. As I mentioned, we're looking at linear functions. Now, I'm going to construct a line of best fit. I'll show you some examples of line of best fit, of points that are plotted. As I showed you earlier, here I have a set of data. Ice cream sales versus temperature. And we plot that on a graph. And then I construct a line of best fit. So here are some other examples of this scatter plot looking at the years. And it means sea level. As you can see over time, the sea level is rising. You can see a pattern here, notice. And you can do that by creating a line, constructing a line of best fit. Now, the other language we're going to use is called interpolation and extrapolation. Interpolation refers to you find the values within a set of data here. So, for example, I can say in 1997, the mean sea level was around -5. Or in 2007, it was 22, or approximately 22, 23 millimeters. So that's interpolating. I'm looking at the data within the given value. Now, if I were to go outside of it, if I were to go beyond this data, I'll be called extrapolating. And if you were to extrapolate, meaning that you're going beyond, go way beyond the set of data, you say that we are extrapolating. So extrapolation, you're going outside of a set of data. So interpolation within the set of data. So this is my set of data here, and I'm reading out temperature versus sales, or extrapolating. I'm saying what would happen if the temperature with 29 degrees? The sales increases? Yes, according to my trend. Now, there are limitations to these. Obviously, if the temperature goes up to 40 degrees, doesn't mean necessarily have more ice cream sales, but so there are limitations to these graphs. We'll look at them later. So here is an slight overview of the different kinds of correlations again. So correlation refers to co and relation. So we have perfect positive, high positive correlation, low positive correlation, no correlation, low negative correlation, high negative correlation, and perfect correlation. So we can have perfect correlation. And notice these numbers here. A correlation is perfect, referred to as 1. And if there's no correlation, referred to as 0, statistically speaking. You have a high positive, might be around 0.9. So it's how close it is. If it's closer to 1, it means that you have a perfect correlation. If it's a little off from 1, we get 0.9. If it's midway, a half. Now, you can find these values, but you'll need to go into a higher level math or do statistics for this. It can be done. And low positive correlation and none. Now, the reverse, now we have a negative. As I mentioned, the y is decreasing now as x increases. So he says it's a low negative, high negative, and perfect negative correlation. So remember, negative correlation means that there's a correlation, but one value goes down as the other value increases. Positive correlation, the y value increases as the x value increases. So here we have a set of data, and you're asked to enter the data and examine the scatter plot. So we plot the graph from the data provided in the table. The table provides data regarding the number of absences per student and the student's final mark. Be sure to include your axis, labels, and scales on each side axis. So number of absences we'll refer to as our x-axis. So we can say there's going to be our x-axis here. And the marks will be our y-axis. Now, look at our values here. We start from 0, and the highest one is 8. So you want to have a reasonable scale that at least cover all of these values. So the minimum value here is 0. The maximum is 8. But this is what the given data is. But if you want to make prediction, you want to go beyond the given data. So we'll make this our x-axis more than 8. You make it 16, 18. So let's look at this. So here, start from 0. And this way, we call this number of absences. So we have 2, 4, 6, 8, 10, 12, or we can make this as 1, 2. Notice I'm numbering these, and the increment must be equal. From 0 to 1, 2, 3. So the increment here is 1. So the increment has to be consistent. You should be going from 0 to 2 to 6 to 10. It has to be equal increments. So we have it 11. Now, our y-axis with the percent of marks. Now, you cannot have more than 100%. So we can safely say that the highest would be 100. So student marks in percentage, we can put here. I'll put in bracket percentage. So tell me that in percentage. So we have 10, 20, 30, 40. Now we can go on to 110, but our highest is 100. Notice this will be 0 here. So we start from 0. Next, we are going to plot our points. So the first absence is 8. The mark is 65%. So I go along my x-axis here, number 8, and I go straight up and find when there is 65. It's about here. And where these two intersect would be my point. So the first one is 8. So I go along my absence here, 8. Then 65, I go all the way up to 65 here, and I just do a little line there. Just it's not part of the graph, just a guide. Tell me that's my point. Next one is 390. So 3, go all the way up here, and 90, which would be this point here. Then 585. So 5 and 85 will be right here. So now this is 5 and this is 85. Next we have 462. So we go along 4 and find 62. So that will be approximately here. Next 087. So 087 would be about close to 90. And 297. So 297 would be. So those are my points, and I plotted them on this plane. So I've labeled the x-axis, the y-axis. Make sure they're equal increments, notice. Now I'll take a ruler or any straight edge, and you want to construct a line of best fit. So remember, you cannot go too far. So now notice that these 2 points here seems to be way out. So you want to construct a line now that will fit, go through as many points as possible. So we'll go to a line of best fit. Now I cannot go above. So a line of best fit. So this will be my line of best fit. So we call this here. Okay. Notice this line is going down. And recall, if we have a line that's going down, we refer to that as a negative correlation. Okay. So if you go back to the world sketch here, if you're going down, it's not perfect, probably high correlation. It's a high negative correlation. So we can say this is a high negative correlation. The emphasis on negative correlation here. Our scale, we have a minimum value. We set that for the x value is 0. The maximum value is set 100 for the x. To the back of the graph. What is the scale? So we have your scale would be 1, right? Because we're going up by 1. So we choose a 1. The maximum, oh, sorry, here we not maximum value of x is 16. We choose 16 here. I was mixing it up with the y value. Okay, let's go to the y value next. So that's the maximum value for the x we have here is 16. You could have done it differently with 2 matrices every other line 1, and that will give you 8 here. That's fine. That could be, that's good. You could make it all the way here and make that 8. That's your maximum value for x. What's the minimum value for y? 0. Maximum value, we're going to make that 100. Because we cannot go above 100. Going to go 100%. But not in a score, a test score. Maximum value for y is 100. The scale, we're going up 10 units. So we're going up scale of 10 units here, or 10%, and 1 absence. So we're going to have an increment of 1 absence in terms of the number of absences, and increment of 10% in terms of the marks. So notice there's a point here. Negative numbers are not needed because we just are using quadrant 1. Remember the previous lesson we learned about the 4 quadrants? And remember we have a Cartesian plane, x, y. We said this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. In this case, we're only dealing with positive values. That is why we only needed this one. Using quadrant 1 here. And the last part, examine the data plot, explain what the data is telling us specifically about the correlation between number of absences and the student mark. It's just showing you that as the number of absences increases, the student marks decreases. So there's a negative correlation. So we can record that. See, as absence increases, students' marks decreases. So we have a negative correlation. So we have a negative correlation in this example. Let's go on to example 2. Plot the graph of the data provided in the table. Here's just a table. The table provides data about the speed of a vehicle and the stopping distance after the brakes are applied. And so remind you, be sure to include your axis labels and scale of each axis. This would refer to as make this your x-axis, because your speed the rate at which you're going will determine the stopping distance. Among other things, the road condition plays a role, but just assuming all things being equal, the time it takes for you to, the distance, your stopping distance, is related to your speed of the vehicle. So the faster you go, in this case here, we'll see what happens. So here we have a speed of 50 kilometers. It takes about 14 meters from the time you apply the brakes for the vehicle to come to a stop. If you're traveling at a speed of 80 kilometers per hour, it will take 30, you will stop, the stopping distance will be 36 meters. In other words, by the time you apply the brakes and the vehicle stopping will be 36 meters in distance. If you're traveling, say, 110 kilometers per hour, your stopping distance would be 68 meters. As you can see, 35 and 150. So let's label our graph. So our x-axis would be speed. So we have here speed. And that will be in kilometers per hour. And always indicate the unit. So we'll start from 0 here. Now notice we have to go to at least up to 150. So we look at our scalar, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have 16, so we have to go up to 150. So if you look at 150, and you divide 150 divided by 16, or let's say we make an increment of 10 or 20. Let's say 150 divided by 10. We might barely make it. Okay, we have 16 here. So we have an increment of 10, 10, 20, 30, 40, 50, 60. 30, 40, 50, 60, 70, 80, 90, 100, 110, 120, 130, 140, 150, 160. It limits us to 160. So it's very difficult for you to make extrapolation. But then again, the speed limit in Manitoba, I think it's 100 kilometers per hour. So on the highway, outside of Manitoba. Outside of Winnipeg, I should say. So we can make this increment of 10. So we have 10, 20, 30. Oops. It's kind of cluttered here. I can make this 20, 40, 60, 80, 100, 10, and 20. 30. Our stopping distance is 126. So we can do the same thing here. We have 20, 40, 60, 80, 100, 120, 100. So we can go up to an increment. So first of all, stopping distance before stopping. This would be in meters. So we have 20, get 0 there. In this case, our minimum x value would be 0. We go back to our question here. We have minimum x value is 0. The maximum x value is 150. Scale on the x-axis would be 10 kilograms per hour. Even though I have numbered increment of 20, this is actually 10. Just so it wouldn't look too clustered. Then the next part asks you for the minimum y value. We said it's 0 meters. Maximum y value here we have 160. And the scale would be 10 meters on your. So that plot our points on the graph. Here we have 50. So we have 50 goes 14, which is about, here's 10. Then we have 80 to 36, 80 all the way up to 36. So I find just 30 here. So 36 would be approximately here. So we go 80. Then you have 60. 20, that's much easier because right on intersecting line. 110, 68. So 110 is here, 68. So 70, so 68 would be so 60 is 60, 70, so 49. So 49 would be here. Close to 10. 30 and 5. $150, $126. So line of best fit through here. You can see this is a positive correlation. So the question, examine the graph of the data that you plotted, explain what the data is telling us specifically about the correlation between the speed of a vehicle and the stopping distance. So the speed of the vehicle and the stopping distance tells you the faster you go, the longer it takes for the car to stop. So we can see here, So we can conclude it's a positive correlation. The higher the speed, the longer is the distance before stopping. So that's the correlation between the two. Now there are two other examples. The number of kilometers page, example 3. Table show the number of kilometers per hour over speed limit and an amount of fines. In this case, there's no grid line given. So you will have to construct your own scale. So I'll complete these here. So in this case here, we start, so kilometers per hour over the speed limit. So this will be your x-axis. And this is your y-axis. So your fines in dollars. Notice I'm using the exact language given in my data or my chart or table in this case. Whatever name label is given in the table, you use that on your graph. And number of kilometers hours over the speed limit, we can write here, number of kilometers per hour over the speed limit. So you can say number of kilometers per hour, or you can simply label as kilometers per hour. Okay. Now notice your x-axis goes up from 5 to 50. So you will start from 0 here. And you want to make an increment of maybe 5. You're going 5 here. So let's say 1, 2, 3. So we have 5, 10, 15, 20. $60, and fines up to 190. So you may want to go up an increment of maybe 20, because your scale is limited here. So let's make this 20, 40, 60, 80, 100, 110, 120. So you have 200. Now you will have to use a ruler because there's no grid lines here. So the first one is 50 and the fine is 190. So I have $50 here. So I'm going to do a straight line. So just do a guide here. And 190, which is horizontal line. So this is my point right here. So here's my 190. So as you can see, without grid lines, it's much more challenging to plot your points. So you will have to use a ruler or a sheet of paper, a straight edge, anything is straight. Next is 10 to 90. So I have my 10 here. And I find 90 is here. No, my scale is not correct. I go up to 20 here. 20, 40, 60, 80, 100. Oops, it should be incorrect scale. Because I'm going over increment of 120 here. 140, 160, 180. Oops. Should have got this all. So 140, 160, 180, 200. So this would be not correct. So those again, you have 0, 24 to 60, 80, 100, 120, 140, 160, 180, 200. This. So 50 and 190 should be here. And you have 10 and 90. 90 will be here. And 25 and 105. Now this is 105 would be approximately at 585. 985 would be. As you can see, we have a limited number of data, so I'm going to construct my line of best fit through as many points as possible. So we can see from here, we have a positive correlation. So as the speed over the speed limit increases, the fine increases. So positive correlation. As the speed over the speed limit increases, the fines increases. Fines increase. Meter here. Okay, your assignment will go on to assignment 2. If you can try assignment 2 on page 9. And also assignment, sorry, this is the first one, assignment 2, question 1. Go back here, my apologies. So question 1, assignment 2. Okay, so question 2, assignment 2, and the third one. I'll take these up in the next lesson. So let's recap what we did today. Our goal is to create and interpret scatterplots and use appropriate scale. We said there are 4 types of correlations. We have a positive correlation. There are patterns between 2 variables. So when you're plotting points between 2 variables, we call it a correlation, how they're related. Positive correlation, whereas the x increases, y increases, and negative correlation, as the x increases, the y decreases. And as the x increases in a constant correlation, the y doesn't change. And no correlation is actually, there's no pattern whatsoever. Then we plotted points. We given us a set of data. We plot points in the graph, and we make sure we have appropriate scale that will cover, that will include all of the data, and possibly more to extrapolate. And your assignment is assignment 2, questions 1 to 3.